So last class we ended by talking about, or I should say briefly talking about P series and how a series of the form from n equals 1 to infinity of 1 over n to the p is going to converge if p is greater than 1, diverges otherwise. Thanks. Welcome. Yeah, also for those of you on Zoom, there's the attendance form. If I was smart, I would do something like put this over here so that when you're walking out, you have it already got it. Or you can do it later. It's not like it's an urgent matter that your life depends upon or anything. Or you can do it right now. So what I want to point out about this is when we say something converges or diverges by because it's a P series, we're specifically referring to this exact format, which is mildly annoying because technically you shouldn't say that this series converges by a P series or because it's a P series. It's essentially the reason why. Really, it's because you can write this as 4 times the series from n equals 3 to infinity of 1 over n cubed. And then, since this series converges, so does this. Welcome. Thank you. I don't want to get too caught up in those details, but that's something someone might care about on occasion. I don't imagine people really would, but some people can be more nitpicky than others. Yeah. Well, so I would hesitate to say this. Like this is a little hand wavy. Because technically a P series is specifically this format. You're starting at n equals 1 and it's a series 1 over n to the p. That's kind of the rationale. But really, we are going to see, or we kind of already can justify it to ourselves, if a series converges, so does a constant multiple. Welcome. Thank you. So here's something worth noting that maybe people haven't said. If some infinite series is convergent or divergent, then so is a non-zero constant multiple of it. Right? If you multiply every term by 5, well, it's still going to add up to either something finite if it was already adding up to something finite, or it's going to add up to something infinite if it was already adding up to something infinite. So multiplying a series by a constant doesn't change its behavior. It's still going to converge if it converged. It's still going to diverge if it diverged. In a similar way, if you have a series and you know it's convergent or you know it's divergent, then so is a series starting anywhere later. So the series starting at n equal to, pick your favorite integer that's larger than 1. If you cut off the first however many terms, the rest of them still either add up to something infinite if it already did, or add to something finite if it already did, right? Subtracting off the first j terms or j minus 1 terms doesn't make a difference. But I should say it doesn't make a difference as far as whether or not the series converges or diverges. Yeah.
So then could you say that any n to the p also does write it as well?
Right, exactly. Yeah. So if I'm looking at the series of, what do you want? Sure. That's definitely convergent. Because it's really this, so this actually is a P series. I'm just going to write it in the usual way. Now, the way we show a P series converges is by the integral test. We're not going to do that. I mean, we could, right? You could definitely show that this converges by showing converges. But the point is we don't have to, because somewhere in the book where your professor has probably shown you at some point, maybe, how to show that this integral converges if P is larger than 1 and diverges if P is less than 1. It's kind of it's a somewhat lengthy proof. It's not like impossible to see, but it's not something I want to spend your time on. So we're going to, I mean, we can later on if you guys really want to, but I think we're probably cool with this. We know this converges. If the power is larger, it's definitely going to converge because you've got smaller terms. And then we know, or we have seen, that this integral diverges. And so it would make sense that something that had larger terms, so we can argue that this, for example, also diverges. The terms are bigger, right? You're dividing by a smaller thing, the terms are bigger. It should be a bigger divergent thing. You could also actually do the integral, right? You could certainly integrate this, take the limit as b goes to infinity, but let's move on to one other thing about these integrals, and then we'll finally start talking about some comparison tests. So the last thing, not the last thing, but the next thing I want to say about integrals and their uses. So sometimes we want to know approximately what a series adds up to, right? Most of these series, geometric series notwithstanding, most of them, we don't know what they actually converge to. For example, now I will say this series, the sum from n equals 1 to infinity of 1 over n squared, is special in that it's been kind of looked at a lot. People know things about it. It does add up to, I don't remember actually what it is. I think it adds up to pi squared divided by 6. I'm not 100% positive on that.
Oh, yeah.
Yeah, it was like, I'm pretty sure pi squared divided by 6. So I'd say converges. And there's kind of a neat proof of this, which if you really wanted to see it, we could talk about in office hours sometimes. It's kind of cool. But that's not the point at this point. What I want to talk about is we're going to try and estimate. Welcome. Love to see your symptom survey when you have a moment. So we start adding up terms. Well, let's just look at the first 4 terms. Thanks. So if we add those up, I'm not going to do the work. It's going to be 205 divided by 144. And this is the 4th partial sum. And it's probably a decent estimate of what this actually adds up to. I mean, right, if you're going to keep adding up terms, right, they're going to get smaller. The things you're adding additionally, each term are going to be smaller and smaller. So we're not going to be off by as much every next term we add. But how much are we off by? Well, let's find out. We can use this to estimate the actual sum. Well, I want to put a bound on the error. So the error, which we're going to call R4, is the rest. Right? So if I actually write this out, sum of 1 over n squared from n equals 1 to infinity, it's 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, et cetera, et cetera, et cetera. And these first 4 terms are the 4th partial sum. And the rest of these terms here are the remainder of the 4th partial sum, which is why we use that notation. And so I want to calculate, or really I want to estimate what this remainder is so that I can have an idea of how close this estimate is to the actual partial sum, or sorry, to the actual sum. So we're trying to answer how good of an estimate S4 is for this sum. Well, let's take a look at some pictures. When we were talking about integrals last class, we were talking about how you could use the area under the curve to kind of give you an estimate of what the sum was. So let's kind of take a look at this. So here's our function, which is a sub n. And if we go out to the nth term, and keep going, so n plus 2, et cetera, et cetera, et cetera. The area here, once again, is a sub n. Right, we're plugging in, I should say f of n is a sub n, sorry. Right, we're plugging in and we're getting a sub n out. That area is a sub n. That's welcome, thank you. A sub n plus 1, etc. So we can see here that the area under this curve from n plus 1 onward. So this area here is an underestimate of a sub n plus 1 plus a sub n plus 2, et cetera, et cetera, et cetera. And if we draw a similar picture, sorry, I'm always running out of room. It's always a challenge for me. But now we draw the under rectangles. So that area is a sub n plus 1. That area is a sub n plus 2, et cetera, et cetera, et cetera. Then the area under the curve here is bigger than what the sum adds up to. Let me see a question. Yeah.
So you're saying that it's underestimated.
Right. So what I'm saying is the integral, which is the red area, is less than the rectangles. And I'm saying here, the integral, which is the red area, is more than the rectangles. And those rectangles are the same, right? That's an plus 1, an plus 2, an plus 3, so on and so on. This is an plus 1, an plus 2, and so on and so on. So what we have is a bound on Rn. We can say that the remainder of the nth partial sum is always going to be between these two intervals. So for our example, if I can move the paper, we could say that R4 has to be between, sorry, I hope you guys can see that, the integral from 5 to infinity of 1 over x squared. Let's give yourself enough room, James, come on. All right, so we're going to say that R4 is between the integral from 5 to infinity of 1 over x squared and 4 to infinity of 1 over x squared. And this is probably where we start to get maybe a little bit lazy about how we calculate these integrals. Technically, you should write out the whole thing. Say, okay, the integral from 4 to infinity of 1 over x squared is, and then we do the whole like limit as b goes to infinity of 4 to b, right? It kind of gets to be a bit tedious. Here's what we end up doing a lot of the time. We know this converges. So what we're probably going to do, what your teacher might have done already, is say, well, I'm just going to kind of take a shortcut. Integral of 1 over x squared is negative 1 over x, and I'm going to evaluate it between 4 and infinity. Technically, right, I should be writing the limit as b goes to infinity, but we know that when I plug in infinity, we're going to get 0. So we're going to get 0 minus negative 1/4, which is 4. Oh, sorry. Yeah, that's a good question. I don't have a great answer. It's really something you probably have to ask them. Yeah. Okay, so then we should really write it out like this. It's going to be the limit as b goes to infinity of the integral of 1 over x squared is negative 1 over x from 4 to b, and then it's the limit as b goes to infinity. I mean, I don't disagree, but also there is a reason to do it, right? Because it's technically, we can't technically just plug in infinity. Now, here's what you can do. Maybe you're not having to show this work when you're actually doing a problem. Maybe you're just trying to see for yourself what something is doing. So you could look at this and be like, well, I know when I plug in infinity to the interval, it's going to be 0. So for work you're turning in on a test, homework assignment, you probably need to show this work. But also for the lots of practice you might be doing on your own, when you get to the stage here and you're looking at this, you can be like, okay, I know it's going to converge because I know when I integrate it, plugging infinity is going to give me 0. And then having done this, I can really easily see what this one's going to be, right? That's definitely going to be 1/5. So we can say with confidence that the remainder, right, the error in our estimate is between 1/5 and 1/4. So to rephrase, when approximating the sum of 1 over n squared as what we have before, 205 over 144, we are off by something between 1/4 and 1/5. I don't know why I started to put parentheses there. Or what I would say really is the error is at most 1/4. Because usually when we're talking about bounding the error for something, we care about how big the error could possibly be. And we'll talk more about that when we start talking about the alternating series test. I think there's one other thing we talk about as far as error is concerned. All right, enough integrals. Let's talk about some other tests like the comparison test. Come on. If I could ever move the paper. So let's see here. So let's look at this series from n equals 1 to infinity of 1 over n to the 4th plus 3. And I should always be thinking about all the tests I have. So currently, here's what we've got. We got the nth term test, regular nth term test. We have geometric series. We have p-test or p-series. We have the integral test. And to me, this looks like I couldn't use any of those. I mean, I could use the nth term test, but it's not going to help me, right? The limit as n goes to infinity of 1 over n to the 4th plus 3 is definitely 0, which means got to do something else. It's certainly not geometric. It's not a p-series, although it looks very similar to a p-series. And I probably couldn't integrate that. That looks like it would be super hard to integrate. 1 over x to the 4th plus 3, like maybe impossible. I don't want to try. Right? I don't want to do the integral test unless I've kind of run out of other options. So even though we learned the integral test kind of early on, as you learn other tests, the integral test should start to become maybe a test of last resort. Kind of like in 21B, partial fractions is kind of like an integration method of last resort. Like you don't really want to use it unless you've tried everything else. I would say the integral test is usually like, save it for if you have to use it. So what we can say here is that our sequence, 1 over n to the 4th plus 3, is definitely less than 1 over n to the 4th. It's always true. At least it's always true for all the n's that matter. It's probably true for all the n's, but certainly for the ones that we care about. Okay, well, if that's the case, then it's also going to be the case that since all the terms are positive, this sum is definitely less than this sum. Right. And we know that this series, sum series, whatever you want to call it, 1 plus 1 over 2 to the 4th plus 1 over 3 to the 4th, we already know this converges. right? This definitely converges. It is a P series. We've got something less than it. Is it convergent? It is, but why? So I'm going to go back to something we said maybe the first or second day of class. We have a sequence of partial sums. That's not the thing, but so if I look at this for a second, my first partial sum is 1 over 1 plus 3. My second partial sum is 1 over 1 plus 3 plus 1 over 2 to the 4th plus 3. My third partial sum is, and so on and so on. Okay, so we know two things about our partial sums. Thing one, they're getting bigger. Each term of my sequence is bigger than the previous one. So my sequence of partial sums is definitely increasing. You know what else we know? It's also bounded because it's less than something that's convergent, right? This thing converges. I don't know what it converges to. I'm sure it's knowable. You probably look it up, but this thing converges. And so it's equal to some finite number. And this series is less than it, meaning it's bounded. And we know a thing about bounded monotonic sequences. They converge. So this sequence of partial sums must also converge because it's a bounded monotonic sequence. Now, the overall gist is that we're going to say if you have a sequence that is less than the sequence that converges, or I should say, if you have a series whose terms of the sequence or whose sequence terms are less than the terms of a sequence for a convergent series, and I'm saying a lot of words, I'm going to write them down in a second, then it's going to converge. So let me actually write down the things instead of just saying the things. So let me go to the next page and we'll come back to that. Yeah. So if the sum of an is less than the sum of bn, and the sum of bn converges, then the sum of an converges. Often there's some maybe more kind of statement about the terms having to all be positive, but this is the gist. If you've got something that's smaller than something else and that something else converges, your thing converges. In a similar way, if the sum of an is bigger than the sum of cn, and the sum of cn diverges, then so does the sum of an. If you're smaller than a convergent thing, you also converge. If you're bigger than a convergent thing, sorry, if you're bigger than a divergent thing, you also diverge. It's kind of it. So the thing about the comparison test, which is what this is that you have to kind of have an idea of whether or not your series converges or diverges in the first place, so that you know to compare it against something that you know converges or diverges in the first place. So let's look at another example. Let's say I have the sum from n equals 2 to infinity of n over n squared minus 1. And this is where I forget who asked me a question, but this particular example here is kind of an answer to the question I was asked via email. Whoever asked it, I don't remember who it was. The idea here is that when I'm looking at a series and the sequence is a rational function, meaning it's powers of n over powers of n, and no other like exponential or logarithms or trig functions. It's just nice rational function. All we're going to do is we're going to look at the highest power in the numerator and the highest power in the denominator. So when I look at this, when I look at n over n squared minus 1, all I see is n over n squared. All the lower power terms are garbage. We don't care about them. The biggest is the most important, right? It's not always true. But in this case, the biggest thing is the most important thing. So this is informing me as to what I should be comparing this against. So I'm thinking, oh, I should compare n over n squared minus 1 against 1 over n. Or what I'm really thinking is, this looks like that, so I'm pretty sure this thing's going to diverge. Because I know the sum of 1 over n is divergent. Now, the problem becomes, if this thing isn't actually bigger than that thing, then I have to work a lot harder. Here, it's not an issue, because it's definitely true that n over n squared minus 1 is bigger than n over n squared, which is equal to 1 over n. No problems here, right? My denominator is smaller, my fraction is bigger. So here we can say, great, this series, n over n squared, converges. Sorry, man, I keep wanting to say the wrong thing. Diverges by direct comparison with the sum of 1 over n from n equals 2 to infinity. Because n over n squared minus 1 is bigger than 1 over n for all n that matter. Again, it's probably true for all n, but it's certainly true for all n bigger than or equal to 2. Now, you might have noticed that I didn't say anything about the fact that I started at 2 here. It's really not a big deal, right? I think most people are perfectly fine with saying, yeah, this is divergent. It doesn't matter that I started at 2 instead of 1, or 5 instead of 1, or 5 billion instead of 1. Or we can start this anywhere, and it's still going to diverge because you're just cutting off a finite number of terms in the beginning. So this is kind of the gist for comparison. If it's a rational function, which we hope it is a lot of the time, we can do this thing. So let's say we have this series, the square root of n over n squared plus 5n plus 15. Well, what should I be comparing this to? Or another question, a similar question, do I think this converges or diverges? Let me ask you guys, actually, so think about what I should compare it to for a second. I'll give you like 10 seconds. It's actually not a second hand on my watch, but I was just like, okay. So thinking about what we should compare it to, raise your hand if you think this is going to diverge. Good. Raise your hand if you think it's going to converge. Oh, I was really psyched because I thought everyone was going to say converge. But raise your hand if you're not sure. Okay, it's also fine to be not sure. So let's think about what we're comparing it against. I'm going to compare with n to the 1/2, that's the highest power of the numerator, over n squared, the highest power of the denominator. Everything else matters less. Right? It's not that these terms don't matter at all, but they don't contribute as much. Right? When n gets really, really large, like if n is 1,000, which I know isn't that big, the denominator is 1,000 squared plus 5,000 plus 15. The 1,000 squared is the only thing that really matters there. Right? That's 1,000,000. The 5,000 and the 15, inconsequential. And they matter even less as n gets larger and larger and larger. So we really, really, really only care about the highest power in the numerator and the denominator. For real, like the other things do not really matter when we're talking about behavior as we go to infinity. So if I simplify my expression here, well, 1/2 minus 2 is -3/2. And I would much rather write that as 1 over n to the positive 3/2. Okay, great. Now, thinking about P series. Is this series divergent or is it convergent? I mean, I like seeing hands raised. It's, you know, it's, I guess it's kind of a teacher thing. Definitely convergence. So that's, oh yeah, question. Question. Or are you raising your hand to be like, different? Okay, yeah. It does not work. So the reason we can't square the entire thing is because you're changing the value. Right? If you square every term, you're going to get something totally different. So for example, the sum from n equals 1 to infinity of n to the 1/2 over n squared, which I'm not simplifying just for the sake of what I'm about to do. If I start writing out terms, I'm going to get 1 over 1 plus the square root of 2 over 4 plus the square root of 3 over 9 plus the square root of 4, which is 2 over 16, et cetera, et cetera, et cetera. Whereas if I square all the terms, so I'm going to get n over n to the 4th, that's going to be 1 over 1 plus 2 over 16 plus 3 over 81. It's not the same. So no, we can't just square a thing without good reason. It's too bad. So, however, we do see that this converges because it's a p-series and the p-value is larger than 1. Right? So often when we're talking about doing comparison, whether it's a limit comparison or a direct comparison, a lot of the time we're comparing against a p-series because we really know how p-series act. We know that if p is larger than 1, converges. We know that if p is less than or equal to 1, diverges. So it's a really easy thing to compare against. So here, I want to compare this with 1 over n to the 3/2. Now, since that's convergent, I'm hoping that the thing I'm comparing this against is actually that this is a smaller thing. And it is, right? The square root of n over n squared plus 5n plus 15 is definitely less than the square root of n over n squared. Right? My denominator got smaller. My fraction got bigger. So we're set. So then we can say, great. Since this converges, we can say that this series also converges by direct comparison. And I would say, I would encourage you to get in the habit of saying what test you're showing convergence or divergence by. Right? If you're saying something converges, it's often a good idea to say by whatever test you used, just so the reader can know what you have done. And let's look at a couple more examples. So the sum from n equals 5 to infinity of n squared over n cubed minus n plus 5. Okay, so I'm looking at that. And I'm thinking of 1 over n, or if you prefer, n squared over n cubed. So I'm thinking of this, which is equal to this. So what I'm really thinking of is, I'm thinking divergence. That's what I'm thinking of. So if I think this diverges, I need to show that it's bigger than something that's divergent. So I need this to be bigger than the thing I'm thinking of comparing against, because that thing is divergent. Or I should say that thing has a series that is divergent. So, well, is this true? Is that bigger than that? It's less nice here because my denominators didn't simply just get smaller, right? My denominator, I subtract like from just like n squared over n cubed. Is it true that n squared over n cubed, which is equal to 1 over n, is that smaller than n squared over n cubed minus n? So the fraction got bigger because I subtracted from the denominator, but now the fraction might not be bigger. but it is in this case. And the way we know it is because we're starting at n equals 5. Since we're starting at n equals 5, the first term definitely, well, if n is 5, you just get n squared over n cubed. We're good. I guess I could say less than or equal to. And then if n is 6, we're good to go, right? Because n squared over n cubed minus 6 plus 5 is n squared over n cubed minus 1. And that's definitely a bigger fraction than n squared over n cubed. So we're good to go here. But you can start to see how it you kind of have to you have to do this manipulation where like, is the thing bigger than the thing I need it to be, or is it smaller than the thing I need it to be? And it's not always ideal. But here we can definitely say that this series of n squared over n cubed minus n plus 5 certainly diverges by direct comparison with the sum from n equals 5 to infinity of 1 over n. All right, let's look at one more and then we will talk about what is, in my opinion, a superior test. Let's look at, I said one, probably two more examples. Oof, all right. The sum from n equals 1 to infinity of the inverse tangent of n over n squared. That looks ridiculous. I would say if the denominator was n squared plus 1, I might try doing an integral test because that would look like a u substitution. I know that sounds kind of weird, but right, if it was instead this inverse tangent of n over n squared plus 1, I might say, well, I know how to integrate that, or at least I think I do. We could do a u sub with u equal to the inverse tangent of x. Kind of bonkers, but that's not what we're doing. And we don't actually need that, even if it was this, which you'll see in just a second. So here's the thing we have to know about inverse tangents, which you might know already. Inverse tangent of n is definitely less than pi over 2. If you recall, the inverse tangent graph has horizontal asymptotes at negative pi over 2 and pi over 2. And it looks like that. Well, great. Then we can say that this sequence inverse tangent of n over n squared is definitely less than pi over 2 over n squared. And then for sure we can say, well, great. I just keep saying great. Then we can certainly say that this sum from n equals 1 to infinity of pi over 2 over n squared, if you really like, you can factor out the pi over 2 and say that this converges. And so by comparison, this series has to converge. One more. He keeps saying. So let's say we had the sum from n equals 3 to infinity of the natural log of n over the square root of n. When you see natural log, at least when I see natural log, I tend to start thinking maybe integral test. And that's because I'm kind of jumping the gun. It's really, really useful to remember some things about the natural log. In this case specifically, that the natural log of n is bigger than 1 for n bigger than e. So I could really straightforwardly say, oh, this series, natural log of n over the square root of n, is definitely bigger than the series 1 over the square root of n. And that's good because this series is . di or convergent? It's divergent, right? It's a p series, right? Where a p is equal to 1/2, which is less than or equal to 1. So again, this is divergent by comparison. All right. So, oh, yeah, we got 10 to 10. So a couple, question. Yes.
If it hadn't worked out quite so well,
Uh-huh.
can you still say that, like, it doesn't matter what happens before 5 because we know the behavior after 5?
Yeah, you can still ignore however many terms in the beginning you need to say what you need to say. Now, really what I would say, I really want to, so here's what I would say. Let's look at something like this. The sum from n equals 2 to infinity of n over n cubed minus 1. I look at that, and if you're me, or if you're you, or if you're me, what series do I really see there? Say it one more time. Which p series? 1 over n to the what? Right. I see 1 over n squared when I look at that, because I'm totally ignoring everything that's not the highest powers. And we know that the series for 1 over n squared converges. So I see a thing that I am almost 100% confident converges. Well, great. The problem with that is this thing here is smaller, sorry, not smaller, it's bigger than n over n cubed, which is 1 over n squared. And that makes it really hard to use the direct comparison test, because there's just not a good, I mean, there are ways to make this work, like, like multiply by 2 and do some other stuff. And usually if you really try hard, you can make it so this is less than something that is convergent. Like you could probably show that n over n cubed minus 1 is less than like 2n over n cubed, which is 2 over n squared. And then that series is convergent. But we don't want to work that hard. It's too much work to figure out what silly arithmetic thing this is less than. Instead, we're going to talk about the limit comparison test, which most of the time is superior to the direct comparison test. There are some instances where it is not. There are definitely some integral, some series where the limit comparison test does not work and the direct comparison test does. But all overall, I would say if I had to choose, I would pick the limit comparison test to try first before trying the direct comparison test in most, if I was thinking comparison at all. So here is the gist. Let the sum of the sequence Bn be some series whose behavior we know. So we know it converges or diverges depending on what we think is happening. And suppose that the limit as n goes to infinity of a sub n over b sub n is equal to L. L is a, well, actually L typically is a non-negative number or infinity. Because usually our terms are always positive. If they're negative, we've got other issues. So then one of two things can happen. If Bn is a convergent series, then An also converges if that limit is not infinity. In other words, if the limit is a finite real number, a finite positive real number, or 0. Another way of saying this is L equals 0 or L is finite positive. And let me talk just for a minute about why we don't want it to be infinity. If this limit, I should say, if this limit is infinity, it means the top thing is a lot bigger than the bottom thing. And if the top thing is a lot bigger than the bottom thing being a convergent series doesn't tell us if the top thing is convergent, right? If you're a lot bigger than something that converges, maybe you diverge, maybe you converge, we don't know. But for example, if this limit was 6, then all you're really saying is that eventually the top thing is like 6 times the bottom thing. And if all the bottom things add up to a finite number, then all the top things are going to add up to essentially 6 times all the bottom things. So as long as this limit's finite, you're good to go. Or 0. 0 is also good because if that limit's 0, you're saying the top thing is less than the bottom thing because that fraction is getting closer and closer to 0. So if you're looking for convergence, you want this limit to be essentially anything but infinity. On the other hand, if the known thing is a divergent series, then the unknown series that you're trying to show converges or diverges is also going to diverge as long as that limit is not 0. So in this case, the limit can be infinity or it can be a finite positive number. And again, let's talk about that for just a second. So if the series for Bn is divergent, that means the terms are adding up to probably something infinite. You can have some weird oscillating stuff sometimes, but let's just restrict ourselves to adding up to infinity. So if these terms add up to infinity, then if the limit's 0, we're going to have a problem. Because the limit's 0, that means these terms are a lot less than these terms. And maybe they're not less in a way where they add up to infinity, but maybe they are. Right? Maybe we don't know. They could be really, really less or just kind of less. Whereas if the limit is infinity, it means the top thing's bigger. And if an is bigger than bn and the bn terms add up to infinity, then the am terms definitely add up to infinity. And likewise, if this limit is something like 6 again, we're just saying the top thing is 6 times the bottom thing. So if the bottom thing's added to infinity, the top thing's added to 6 times infinity. We're good to go. So essentially, the limit comparison test says if the limit is a finite positive number, the top thing and the bottom thing do the same thing, meaning they either both converge or they both diverge. And then specifically, if you're looking for convergence, it's okay for the limit to be 0. If you're looking for divergence, it's okay for the limit to be infinity. It's a little touchy there. So with that in mind, we can really now just think about what the highest power in the top and the bottom is. So for example, if I am looking at the sum from n equals 2 to infinity of n over n cubed minus 1, I'm going to limit compare this with 1 over n squared. I should really say with the series for 1 over n squared. When you're doing limit comparison, it's always the unknown sequence on top and the known sequence on the bottom. So that's the known one, right? We know this converges. So before we're even using the test, we already think we know what's going to happen. We are pretty sure this series is convergent. That's why we're comparing it with something that's convergent. And I should really kind of emphasize, the direct comparison test and the limit comparison test are both tests where you first have to have an idea of what happens so that you know what to compare it against. Versus later on, the ratio and the root test are tests where you don't have to know what you think happens. You just apply the test and the results, if they're conclusive, tell you what happens. So here, we're going to do the limit as n goes to infinity of the unknown over the known. Now, you're going to get real tired of writing that when you're always going to flip and multiply. So I would encourage you all to kind of skip the first step and write it as the unknown series sequence multiplied by the reciprocal of the known sequence. And then we get the limit as n goes to infinity of n cubed over n cubed minus 1. Who needs L'Hopital's rule? We know that's 1. Because the power on top and the power on the bottom are the same. The limit is the quotient of the leading coefficients, which is 1 over 1. Which means the unknown series also converges. I like using the word also there to really kind of emphasize the fact that we had to know that the first one converged to say that the second one also converged. Questions, comments, thoughts? Let's look at more examples. So, I got time. So let's say we had this series, the series from n equals 1 to infinity of the square root of n minus the 1/2 over 4n plus 1. And once things start getting complicated, I don't even want to think about direct comparison. I'm just like, I could maybe compare this. No, I don't want to. It's probably smaller, right? So I'm thinking, well, I'm thinking that this does something because I'm going to compare it to, I'm going to limit compare it to, well, what am I limit comparing it to? N to the 1/2 over n, or the sum of that. Technically, you're comparing a series with another series, which is why I should really write that. But yeah, I should be precise. So that's going to be the sum of 1 over n to the 1/2. So we're thinking that this diverges because we're going to limit compare it with something that diverges. And so what I should say is that limit comparison will always work if your series, if the sequence for your series is a rational function. Meaning if you just have powers of n over powers of n, you really shouldn't even think of anything else. Powers of n over powers of n, automatically limit comparison test is the way you want to go. Unless there's something else that's even easier, that's more obvious. But really, like, limit comparison is the way to go for rational functions. Or even this, actually technically this isn't a rational function because the power isn't a integer power. So any power of your variable, good to go. So I'm going to do the limit as n goes to infinity of the unknown thing, n to the 1/2 minus 1/2 over 4n plus 1. And instead of dividing by the known thing, I'm going to multiply by the reciprocal. Just to save myself a step. Multiply it out. The limit is n goes to infinity of n to the first minus 1/2 n to the 1/2 over 4n plus 1. Again, you could use L'Hopital's rule here, but really, if you have positive powers over positive powers, you look at the highest powers and the quotient of the leading coefficients is what you get. So this limit is definitely going to be 1/4. Or, right, or L'Hopital, or if you really want to go back to 21A, or you could divide everything by n. Or whatever the highest power of n is. In this case, it's just n to the first. All those will work. Your teacher probably doesn't care a lot about how you evaluate this limit as long as you're able to evaluate it. So this is a not 0, not infinity, right? Those are the two things I think about. As long as it's not 0, not infinity, I don't really have to think that much harder. I know they do the same thing. So that means great. Our series also diverges. Oh yeah, those are some good ones. Let's look at some. So the rational function ones get to be kind of boring, right? Like I'm not going to do it, but you all could totally look at this series. I don't know, let's say 2n cubed plus 4n plus 1 over 6n to the, I don't know, 4.2 plus 7n squared minus 8 And without a whole lot of effort, we could all show that this, by limit comparison with, what am I going to limit compare it to? Highest power, highest power. So I'm thinking that this series would do what? If I'm comparing it to the sum of 1 over n to the 1.2. I know 1.2 is not like a typical power that we see. Still convergent, right? P series, our power is bigger than 1. So we're thinking that this, or we can show that this converges by limit comparison with that. And then you would, I said, like, here's me not doing the problem. Right, we would do this. You multiply by n to the 1.2 over 1, and then you have the limit n goes to infinity of 2n to the 4.2 plus 4n to the 2.2 plus n to the 1.2, which is mildly annoying, but not that bad. And then, oh yeah, that's going to be 2/6. So things where you just have powers of n over powers of n, you can always use a limit comparison test, and it becomes pretty straightforward. So let's look at some less straightforward examples, like sum. Which one do I want to do first? They're both so fun. Let's do this one. Sum from n equals 1 to infinity of sine of 1 over n. This is a classic hard, easy question, or easy, hard question, meaning it's really hard until you know how to do it. And then it's pretty straightforward, but not until you know how to do it. So looking at this, if I didn't know what, like, if I wasn't like in the limit comparison text section of the textbook, I'd be like, how am I going to show that that either converges or diverges? Well, I'd probably start with the nth term test, because that's always a good place to start. Sometimes you get some free stuff, right? Nth term test is just like, take the limit. Maybe you're going to get lucky and it's not going to be 0. Like, for example, well, in fact, just so here it is 0, right? Limit as n goes to infinity of sine of 1 over n is 0. But I have definitely seen, does this series converge or diverge on a test? And that one you all should easily be able to say, oh, it diverges, because what's the limit of the sequence? Oh, sorry, it says the sum from n equals 1 to infinity of cosine of 1 over n. So the limit as n goes to infinity of the sequence is, which is? Right, which is not 0, which means this diverges. So sometimes you get some pretty free, I mean, I think of that as a free answer, because like you almost did hardly any work. So you should always be somewhere in the back, right? Like, should I try the nth term test? I should just think really quick. What's the limit of that sequence? Is it 0? Oh, it's 0. Okay, do something else. Oh, it's not 0. Great, I'm done. That series diverges. But this one, unfortunately, the limit is 0, so we need to do more. So we're going to do a limit comparison here. We're going to limit compare this with 1 over n. I should really say with the sum of 1 over n. Okay, so we are going to do, which we know diverges. So we're going to do the limit as n goes to infinity of the unknown sequence over the known sequence. And this one you actually don't want to flip and multiply like I've been doing for the other ones. So there's a couple ways to see. You can use L'Hopital's rule is probably the way you should go here. But you might remember from 21A that the limit as theta goes to 0 of sine of theta over theta is equal to what? So you might remember. It's a very important limit. That equals 1. Or you might see it using x's, right? Limit as x goes to 0, sine x over x equals 1. Well, we have the same sort of thing here. we have the limit as 1 over n goes to 0 of sine of 1 over n over 1 over n. That limit is 1. Now, it's probably easier to see using L'Hopital's rule. We definitely do have a 0 over 0 type of limit. So using L'Hopital's rule, we're going to get, well, the derivative of sine of 1 over n is cosine of your stuff times the derivative of your stuff. And the bottom, well, the derivative of 1 over n is also negative 1 over n squared. And look, these cancel, and the limit as n goes to infinity of cosine of 1 over n is cosine of 0, which is 1. So since this limit is not 0 and not infinity, specifically in this case, not 0, because we were looking for divergence, so infinity would have been fine. But since this limit is not 0, we can say the series we started with diverges. Kind of cool. I've definitely seen this question on tests as well. It's definitely harder than that one. Let me show you a similar question. It's a little bit different. Or in fact, let me just point out. In a similar way, we could show that the sum from n equals 1 to infinity of sine of 1 over n squared converges. You could literally do the same work. In fact, we might as well do it. So we're going to do a limit comparison with this convergence series. And we're going to get the same thing happening. Oh, not at all. Sorry. Yes, please don't hesitate to ask if the paper is. Yep. Thank you. Also on the chat. Yeah. Now we're good. Okay. So we're going to do the limit as n goes to infinity, unknown thing over known thing. And if you were looking at the previous problem, you can probably see here, well, looks like if I use L'Hopital's rule, the same sort of thing is going to happen. When I take the derivative of the top, I'm not even going to write out the whole thing. I mean, I am, but like not really. The derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. Yes, I know we know what the derivative of 1 over n squared is, but it's really feeling like I don't want to write it. And the reason I'm really saying that is because I'm making the observation that when you take the derivative of the bottom, those are going to cancel. The derivative of 1 over n squared and the derivative of 1 over n squared divided by each other cancel each other out. Yes, they would be negative 2 over n cubed, but I think you all agree with that. And then that's going to be the limit as n goes to infinity of cosine of 1 over n squared, which is certainly cosine of 0, which is 1. And since here my limit is not infinity, right, because I'm trying to show convergence this time. So since my limit is a not infinity, then we can say that this series also converges. Kind of cool. Yeah, what else? Sure. Yeah. Okay, yeah, let me go back to this. There was one other thing I wanted to see. So some things to be aware of for natural log, because I think it's worthwhile. So I would definitely encourage everyone to be aware of this fact. The natural log of x is less than x to any positive power. Graphically, I think you guys probably agree with me. So here's natural log of x. Something like that. It grows really slowly. It does go to infinity, but like super duper slow. The only thing that goes even slower, well, not the only thing, but one thing, if you're looking for an interesting time on Desmos, graph natural log of x. It does also go to infinity, but like looks like a flat line. Like it does like very slowly, bigger, but it's really taking its time. I think I remember hearing someone say like, if you added up all the terms of the sequence where like from n equals 1 to infinity, or from n equals 1 to the number of seconds that have elapsed from the beginning of time until now of the sequence of like, I think it was the natural log of n, you get like 40. Like there's like, it's so slow. Like it goes to infinity, but it takes so long. Anyway, that's not the point here. The point here is that here's y equals x to the 1. Definitely bigger. And clearly x to larger powers is going to grow even faster, but even fractional powers, right? Like the square root of x or the cube root of x, which I'm not good at drawing, but does this kind of deal. Okay, you'll just have to believe me. I would say graph these on Desmos. Graph and compare on Desmos. That the square root of x is bigger than the cube root of x, is bigger than other powers of x, like x to the 1 over a positive number, bigger than the natural log of x. Natural log of x is super slow, and any root of x will always eventually outpace it. Maybe not at the very beginning. Like I feel like you might be able to figure something out where the natural log was bigger for like a split second, but any 10th root of x, 100th root of x, whatever, always eventually going to be bigger than the logarithm, which is great. It's helpful. So with that in mind, we can think about things like the sum from n equals 1 to infinity of 1 over n times the natural log of n. This one is not my favorite. And it's not my favorite because it's kind of hard. I mean, if I was going to try to compare this with, well, first of all, even though I could probably use direct comparison, I'd rather use limit comparison. So at least I think I would, he says before he actually does the problem. I don't have it written down here. I'm just going like, this is a good problem. Now, I know for sure we could use the integral test. The integral test would definitely work here. In fact, it might be what we actually need to use. Let's look at some examples. So if we limit compare this with, say, 1 over n, then we're going to get the limit as n goes to infinity of the unknown over the known. We should rewrite that as the limit as n goes to infinity of 1 over natural log of n. Oh, that's going to be 0, which is not good because we were looking for divergence. If you're looking for divergence, 0 is the only thing you don't want. We might try 1 over n squared, which is convergent. But if we do that, things are also not going to work out. 1 over n times natural log of n times n squared over 1. That's the limit as n goes to infinity of n over natural log of n, which if we use L'Hopital's rule is going to definitely be infinity. Or you can even just say n is clearly bigger than natural log of n. So this fraction definitely gets larger and larger and larger. Again, not what we wanted, right? We were trying to show convergence and we got infinity. That's not okay. It's not going to, it's inconclusive. So what I should say is both of these are inconclusive. At this point, I might try one more thing before going to the dreaded integral test. Often a good choice, a thing that you might say that natural log kind of acts like, is often natural log can be compared with the square root of n. It's often a good substitute if you're trying to make something work. I still don't think it's actually going to work here, but let's see really quick. So if I did that, I would be doing a limit comparison with the sum of 1 over n times root n, which is 1 over n to the 3/2. I'm not feeling very good about this. So when I do this, let's see. We're going to get the limit as n goes to infinity of 1 over n natural log of n. Divided by that is multiplied by the reciprocal. It looks bad. It looks real bad. Because now I have n to the 1/2 over the natural log of n, which is definitely going to go to infinity. Is it going to go to infinity? Let's check. I mean, it should by what we just said, right? We know the square root is way bigger than the natural log eventually. But if we use L'Hopital's rule, we get 1/2 times n to the minus 1/2 over 1 over n. And then if we multiply by n, oh yeah, we're getting the limit as n goes to infinity of 1/2 times n to the minus 1/2 times n to the 1, which is the limit as n goes to infinity of 1/2 n to the 1/2. Well, shoot, I think we're stuck with the integral test here. So sometimes limit comparison doesn't work. And I don't think direct comparison will work either here, because I'm pretty confident this one diverges. So let's check out the integral test. So we've got the sum of 1 over n natural log of n. And I may have made a slight error when I wrote this one down. I did write something kind of terrible here, which is that I wrote that it started at 1. That's really not correct, because if it starts at 1, what's your first term? Dividing by 0. Let's start that at 2. Okay. So we're going to look at the integral from 2 to infinity of 1 over x natural log of x. And yes, we should do it the correct and proper way. It's going to be the limit as b goes to infinity of the integral from 2 to b of 1 over x natural log of x dx. Now, I really don't like doing a u sub where I have both a limit and limits of integration. Like, it's just gross. So if I was doing this integral, what I would do is off to the side, I would just do the indefinite integral. So I'm doing the integral of 1 over x natural log of x. I'm going to let u equal natural log of x. And my du is going to be 1 over x dx. So this is going to turn into, so let's see, my 1 over x dx is my du. And I'm left with a 1 over u. Integral of 1 over u is the natural log of the absolute value of u. And then that's the natural log of the absolute value of the natural log of x. So there's your antiderivative of 1 over x natural log of x. It's natural log of the absolute value of natural log of x. Okay, so then we can just jam that in here and say I've got the limit as b goes to infinity of the integral of that, which is the natural log of the absolute value of the natural log of x from 2 to b. And then we plug in the limits of integration. We actually do need, no, we don't. Never mind. Take it back completely. So as b goes to infinity, the natural log of b goes to infinity. And as the natural log of b goes to infinity, the natural log of that goes to infinity. So this definitely goes to infinity, which means this series diverges. And this might be the only way to show this diverges. I don't know if there's another test that actually will also show that. If there is a limit comparison, I don't know what we would limit compare it to. It's 254. Let's see. Yeah, maybe. Oh, after last time.
This one.
Oh, sure. We can definitely look at one like that. Okay, so let's say we had something like, but not wholly the same as, the sum from n equals 1 to infinity of, sure, 4x cubed over the square root of x to the 8th plus 9x squared. Sure, that looks nice and terrible, but similar to what you've got. So, oh, except I should be using n's, not x's, sorry. Got carried away. So what's our gut? What do we think is happening here? Well, I'm looking at this and I'm thinking I have something like highest power in the numerator, highest power in the denominator. Sorry, and if you can't read what I've written because I've terribly scratched that, that's an n to the 8th plus a 9n squared, and it's in the square root. So what's the highest power in the denominator? Right. So I'm pretty sure that this is going to diverge. And I'm going to use the limit comparison test to show it. So I'm going to do the limit as n goes to infinity of 4n cubed over the square root of n to the 8th plus 9n squared times n over 1. Okay. So that's the limit as n goes to infinity of 4n to the 4th over the square root of n to the 8th plus 9n squared. Now here is a time where L'Hopital's rule is not your friend. L'Hopital's rule here is going to probably result in this kind of endless loop where the denominator becomes the numerator and then becomes the denominator, and you just go back and forth and it never kind of resolves. Something to know about that is that happens, it means your limit is going to be probably 1 or something close to 1, depending on what you've got. But the way we can deal with this in a less terrible way is by having more paper, is by kind of going old school, saying, I'm going to go back to like 21A methods. And instead of trying to use L'Hopital's rule, I'm going to factor out something in the square root. I'm going to factor out an n to the 8th. Or whatever the biggest power is in general. So I factor out an n to the 8th. I'm left with a 1 plus 9 over n to the 6th. And now, what's the square root of n to the 8th? Right. Now, I should be a little more specific here. That is true here. The square root of n to the 8th is n to the 4th because n is, because n is positive. But more generally, the square root of n to the 8th is almost the absolute value of it. Well, it's a different thing. It's the absolute value of n to the 4th. So if n is positive, great, your result's positive. But if n is negative, negative number raised to the 8th power is positive, and the square root of that is the positive result. Here it doesn't matter because we're taking the limit as n goes to infinity. So our numbers are positive anyway, it's not a big deal. But I just really wanted to be careful, right? If you see this, right, it's really important that you know it's equal to that, not just x. Oh, yeah, you're like, what are you saying? That. I've obviously zoomed in too much. So to deal with this, that square root of n to the 8th is going to become n to the 4th times the square root of 1 plus 9 over n to the 6th. And then things work out great. The n to the 4ths cancel. And then we're left with the limit as n goes to infinity of 4 over the square root of 1 plus 9 over n to the 6th. The 9 over n to the 6th goes to 0. You get 4 over the square root of 1, which is 4, which is not 0 and not infinity, which means they do the same thing. So looking back at where we started, this means that this series diverges because the limit comparison test gave us a number that wasn't 0 specifically. Question? I would say that that depends on what your teacher is saying in class. So maybe like I think it's certainly true that essentially this series for all important purposes, this is acting like this series, which is that might not be rigorous enough for some people though. So this I know for sure right? Doing this work definitely actually shows that the series is divergent with a tried and true limit comparison test. Whereas saying this, although true, might not be enough work for some people. But it depends on who your teacher is. All right, it's 3 o'clock. I should stop talking.